today we are finally getting into actual probability, not just counting things, but actual probability. Probability is the likelihood or the chance of an event occurring. It's a decimal from 0 to 1. We can express it as a decimal, we can express it as a fraction, or as a percent. So this little chart just shows from 0 to 1, written as fractions, decimals, and percents. A probability of 0 means that it's impossible. It's not going to happen. A probability of 100% or 1 means it's definitely going to happen. Like if I'm standing outside in the middle of a rainstorm and I say the probability of it raining today is 100% as it's currently raining on me. That's definitely certain it's going to happen. The first thing we're going to talk about is theoretical probability. Theoretical probability is basically what should happen according to statistics and numbers and how things work. Like, I think you all probably know this already. What's the probability of flipping heads on a standard coin? 50%, because you've got heads, tails, 1 out of 2, 50%. So the probability is the number of outcomes, the number of things that you want over the total number of outcomes. So in the flipping coin instance, we want heads. There's 1 outcome that we want. There's 2 possible outcomes, heads or tails, so 1 over 2. What is the probability of flipping a coin and getting tails? We basically just answered that. It is 1 out of 2, which is the same as 0.5, which is the same as 50%. Rolling a number greater than 2 on a standard 6-sided die. So die is the word that means like a singular of dice. Standard 6-sided die means that it's got the numbers 1 through 6 on it, and it's not weighted or cheating in any way. So we want a number greater than 2. Does it say greater than or equal to, or just greater than? Greater than. So we'd be okay with 3, 4, 5, or 6. That's 4 outcomes that we want out of 6 possible outcomes. We can grab a calculator to actually figure out what that decimal is. In some classes, I ask them to write the decimal, like the fraction, the decimal, and the percent. If you just want to write the decimal, that's fine. So 0.67. Rolling a number less than 7 on a standard 6-sided die. I want you to think about that for a minute. What numbers are on a die? 1, 2, 3, 4, 5, 6. How many of those are less than 7? All of them. So there's 6 things that we'd want out of 6 possible things. That would be 1. So the probability of rolling a number less than 7 on a 6-sided die, it's high. It's very high. It's like certain even. A long time ago, I started teaching probability and talking about a standard 52 card deck, and about 2 days in, realized half of my class had never actually played with a deck of cards and didn't really know what I was talking about. So this is a standard 52 card deck of cards. It has aces, which we're going to call aces 1s. So you might want to jot a little note that an ace is considered a 1. So if we talk about numbers less than 7, we'd be talking about 6, 5, 4, 3, 2, and aces. So 1 through 10, aces through 10. And then the face cards are jacks, queens, and kings. So I'm going to outline these cards up here and call these the face cards. If you actually look at these cards, they have faces on them. They're like little people. There's 4 suits. Each of these columns is called a suit. This first column is spades. The next is clubs. Then we have the red cards. We have diamonds and hearts. One card is randomly drawn from a standard 52 card deck. Find the probability of drawing the 7 of spades. So, the 7 of spades, that's one thing we want out of 52 cards total. So 1 divided by 52, we have a 0.02 if we round, 0.02 chance. That's a 2% chance of drawing the 7 of spades. How about a diamond? It could be any diamond. Anyone know how many diamonds there are there? There's 1 through 10 plus 3 face cards. That's 13 out of 52. Which, by the way, simplifies to 1/4. Does it make sense? If there's 4 suits, we're wanting anything from one of the suits, 1 out of the 4 suits. This ends up being 0.25. You have a 25% chance of getting a diamond. A red face card. How many red face cards are there? There's Jack, Queen, King of diamonds, Jack, Queen, King of hearts, so there's 6 of them. That is a 0.12 if we round, a 12% probability. I want you to see if you can do D and E on your own. So count up how many things match that description out of 52 and then change it to a decimal. The King of Hearts or King of Diamonds, that's 2 cards out of 52. 2 out of 52 is a 0.04, so a 4% chance. A card less than 5, including aces. It says less than, not less than or equal to, so we're talking about 4 down through the aces. That's 16 cards out of 52. It would help if I divided correctly. That's about a 31% chance, 0.31. So write it as the fraction and then find the decimal. You can just leave your answer as the decimal. You don't need to actually go to the percent if you don't want to. But do at least go from fraction to decimal because it's easier to compare numbers when they're all decimals. Fractions are harder to compare than decimals. And if you have it in decimal form, you could easily change that to a percent if you wanted to. All right, you have this in your notes, so if you ever are referring to a standard deck of cards and you need help with picturing that, this is in your notes to help you. On the next page, this is kind of why we did the first 2 days of the probability unit first. You have a playlist of 8 songs. You set the player to random. What is the probability that the songs are played in the same order they are listed in the playlist? So, 8 songs, we want to find out, first of all, how many ways could those songs play? That's a permutation. That's 8 factorial. So do 8 factorial to find how many ways these songs could be played. There are 40,320 ways that those songs could play. There's that many different orders of the playlist. We want the one way that it's listed in the playlist. That's the one that we want out of the 40,320 options. What you get in your calculator? I'm going to just write it out. 2.48015873 times 10 to the negative 5th. 10 to the negative 5th means that you're moving the decimal to the left 5 times. So this is actually 0.1234. 1, 2, 3, 4, 5. Yep. 248. It's this crazy small number. If you want to, on your notes or on your assignments for this type of a problem, if you wanted to write 2.48 times 10 to the negative fifth, that would be okay. Just realize that this is a very, very, very tiny number. If we change this to a percent, it would still be 0.00248%. So the chances of your music player actually playing it in the order listed is very, very, very rare. Okay, everything we've been doing so far is theoretical probability. Basically, it's what should happen according to the numbers. But then there's experimental probability. Experimental probability is using what actually happened. So, in experimental probability, you've got your number of successes, the number of things that you want that actually happened over the total number of times that you tried. A spinner has 5 equal sections colored red, green, blue, yellow, and purple. The table shows the result of 50 spins. Find the experimental probability of spinning each color, and then find the theoretical probability for spinning each color. So for experimental probability, we got red 5 times. 5 times out of 50. 5 out of 50 is 0.1. We got green 20 times. That's 20 out of 50, which is 0.4. Take a moment and find the rest of those experimental probabilities. So each of the numbers, the spinner results divided by 50, we got 0.1, 0.4, 0.06, 0.2, and 0.24. So which color what was more likely to happen according to our experiment? The green occurred most. So I don't know if maybe the spinner wasn't placed on a random place before spinning. Maybe the person who was spinning it happened to just flick it in such a way that it landed on green more often. Maybe it's a difference between a right-handed person and a left-handed person. Maybe the spinner's spinner, the little thing that actually spins, maybe it was like weighted funny. What should the probability of spinning red be? We want red. There's 5 sections that are all equal. 1/5 is 0.2. The probability for green should be 0.2. All of these should be equally likely, but just because they're equally likely doesn't mean that they're actually going to be equally occurring when we do an experiment.